There are some questions that feel almost too small to matter. They arrive quietly, wearing ordinary words. And because the words seem familiar, we assume the question itself must be familiar too. We think we already know the shape of it. We think we already understand what is being asked. And then, if we stay with it long enough, something begins to change. The edges soften. The meaning deepens. And what once looked like a simple idea begins opening into one of the strangest landscapes in science. Nothing is one of those ideas. At first, it sounds effortless. Nothing should mean emptiness, no matter, no stars, no dust, no motion, no light, no energy, no structure, no thing at all, just a blank absence. It sounds clear. It sounds clean. It sounds like the sort of concept a child could understand in a moment. And yet, the moment physics begins to examine that word carefully, it starts to resist us. Because in science, and especially in modern physics, nothing is not nearly as empty as it first appears. Imagine a room, not a dramatic room, not an ancient temple or a sealed chamber in a laboratory, just an ordinary room in an ordinary building at the end of a quiet day. The chairs have been taken away, the shelves are bare, the curtains are gone, the floor has been cleaned, every visible object has been removed, the air feels still, the silence feels complete. You stand at the doorway and say, "The room is empty." And for the purposes of life, that is a perfectly good sentence. But for physics, it is only the beginning of a sentence. Because the room is still full of air, unless that too is removed. It is still full of thermal radiation from the walls, full of atoms vibrating in the floor, the ceiling, the glass of the window, the paint, the metal in the hinges. It is full of electromagnetic fields, full of gravity, full of invisible structure so familiar that our senses no longer register it as presence. So, let us make the room emptier, seal it tightly, cool it, pump out the air until almost every molecule is gone. Now the room is emptier than before, but still not empty. Light may still find its way in. Radiation is still present. The walls still contain matter. Fields still occupy the space. And once we begin looking through the lens of quantum theory, even this near vacuum is no longer still in the way classical imagination once hoped it might be. Something remains. Something always seems to remain. And that quiet persistence turns out to matter more than we first expect. Because what we call nothing in ordinary language, and what physicists mean by nothing, are rarely the same thing. Tonight, we will move slowly through that difference. We will begin with the ordinary human idea of emptiness. Then, we will pass into the vacuum of early science, into the quantum vacuum of modern theory, into the strange world of fields and fluctuations, into the hidden energy of empty space, into Einstein's dynamic spacetime, into the expanding universe, the Big Bang, inflation, the origins of galaxies, the puzzle of time, the strange accounting of cosmic energy, and finally, the frontier where our deepest theories still fall quiet. And through all of it, we will keep returning to one small sentence. When physicists say nothing, what do they actually mean? To begin answering that, we need a distinction that is simple in wording and profound in consequence. There is philosophical nothing, and there is physical nothing. Philosophical nothing is absolute absence. No matter, no radiation, no fields, no vacuum, no space, no time, no laws of physics, no possibility of events, no geometry, no potential. Not an empty universe, but the absence of any universe whatsoever. Not darkness, because darkness already suggests a place in which light could fail to appear. Not silence, because silence already suggests time passing without sound. Philosophical, nothing is more radical than emptiness. It is non-existence in the strictest conceivable sense. This idea belongs to one of the oldest questions ever asked. Why is there something rather than nothing? It is an extraordinary question, but it is also a difficult one for physics, because physics is a discipline that describes relations, structures, changes, laws, and measurable patterns. If there is no time, no space, no law, no field, no structure of any kind, then it is hard to see what tools physics would even use to describe that state. Physics is powerful, but it is not magic. It needs something to model, something to compare, something to define. Physical nothing is different. Physical nothing is the emptiest state that physics can meaningfully describe, not the absence of all reality, but the lowest, barest, quietest condition allowed within a physical framework. It is the closest science can come to emptiness while still remaining inside the language of science. That difference changes everything. Because once we shift from philosophical nothing to physical nothing, the question becomes less like an impossible paradox and more like a doorway into cosmology. We are no longer asking how absolute non-being could somehow give rise to stars and galaxies. We are asking whether the quietest possible physical state might still contain hidden structure, hidden potential, or hidden rules from which a universe like ours could emerge. That is still a deep question, but it is no longer a question beyond all description. And once we ask it that way, the first place we are led is the vacuum. For a very long time, the vacuum was not a simple idea. Ancient thinkers argued over whether empty space could exist at all. Aristotle believed that nature abhorred a vacuum. To him, a true void was not something the world would permit. Matter would rush in. Emptiness would collapse. The world resisted gaps. It is easy to hear that from the modern world and assume it was merely naive. But in fairness, it was not a ridiculous intuition. In daily life, emptiness is difficult to find. Air fills rooms, water flows into openings, dust settles. The world around us seems almost eager to occupy every available space. If you tear open a container, air enters. If you dig a hole below water, it fills. The old intuition that voids are hard to sustain came from careful observation of the ordinary world. What changed was the rise of experiment. With barometers, pumps, sealed chambers, and improved measurements, scientists learned that air has weight, pressure can be measured, and low-pressure spaces can be created. Torricelli, Pascal, and others showed that what had seemed like a philosophical impossibility could be approached physically. A vacuum, at least in the practical sense, was real. But even a laboratory vacuum was not absolute emptiness. It was only emptier than the world outside. That distinction has followed physics ever since. A vacuum chamber can remove almost all gas from a volume. It can become so sparse that by everyday standards it seems perfectly empty. And yet it is not free of everything. A few molecules remain. Radiation remains. The chamber walls are made of atoms whose thermal motion continues. Fields remain. Gravity remains. The chamber becomes quiet, but not null. That was already enough to complicate the everyday meaning of nothing. Then quantum mechanics arrived, and the vacuum changed forever. Modern physics does not speak only in terms of particles moving around inside a blank background. At its deepest successful level, it speaks in terms of fields. This shift is easy to say and hard to fully feel, because human intuition tends to prefer objects. We imagine the world built from tiny things, little pieces, little bits of matter with positions and trajectories. That image is not useless, but it is not the deepest one modern theory offers. In quantum field theory, the universe is filled with fields. The electromagnetic field exists throughout space. So does the electron field. So do quark fields, neutrino fields, gluon fields, and the Higgs field. A particle is then understood not as a self-sufficient object drifting through an empty void, but as a localized excitation of a field. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Matter, in this sense, is what fields look like when they become excited in certain stable, measurable ways. This matters enormously for our question, because once fields become fundamental, empty space stops being a blank stage. Even if you remove every particle from a region, the fields remain. You can clear a room of furniture. You can pump a chamber free of air. You can imagine a region with no real particles crossing it. But you do not remove the fields in the same way, because they are part of the underlying physical description of the world itself. So what is a vacuum now? A vacuum is not a place with no fields. It is the lowest energy state of those fields. That is already stranger than the everyday word empty. But quantum theory adds one more surprise. The fields cannot be perfectly still. This is tied to the uncertainty principle, though not always in the simple textbook way it is first introduced. The point is not merely that we cannot know certain pairs of quantities exactly at the same time. The deeper point is that quantum systems do not settle into the perfectly silent, perfectly motionless calm that classical intuition once imagined. A field in its lowest state still fluctuates. The vacuum is quiet, but it is not dead quiet. It is calm, but not absolutely still. If we need an image, we might imagine a lake before sunrise. From the shore it looks smooth, almost glass-like, a still surface, a pure stillness. But look longer and more carefully, and you begin to notice motion, tiny ripples, subtle shifting, a tremor too faint to matter to ordinary sight, yet present nonetheless. The quantum vacuum is not a lake, of course. It is not a fluid in any ordinary sense. But this image helps us hold one essential idea. The lowest state of reality is not absolute stillness. Something remains, something fluctuates, and from those fluctuations, consequences follow. This is where the famous idea of virtual particles often enters the conversation. The name is vivid, and because it is vivid, it often causes confusion. It suggests little particles literally popping in and out of existence in a way that sounds almost like magic. That picture can be useful at a rough level, but it should be handled carefully. A better way to think about it is this. Quantum fields fluctuate. Those fluctuations can be represented mathematically in ways that look like temporary particle-like excitations or exchanges. These are called virtual particles, but they are not particles in the ordinary sense of objects you isolate, detect directly, and watch travel through space for an extended time. They are part of the internal structure of interactions. Still, their effects are real. They are not poetic inventions. They are part of the reason our calculations match experiments. One of the most delicate and beautiful demonstrations of this is the Casimir effect. Place two uncharged metal plates extremely close together in a vacuum. Classical reasoning would suggest very little should happen. No charge, no visible force, just two neutral objects with an empty-looking gap between them. But the vacuum is not simply empty. The presence of the plates changes which vacuum fluctuations can exist between them. Outside the gap, more fluctuation modes are possible. Inside, fewer are allowed. This difference creates a tiny pressure imbalance, and the plates are gently pushed toward one another. Something that appears to be empty space produces a measurable force. Not metaphorically. Actually, the effect is small, but that is part of its beauty. The universe is not shouting here, it is whispering. It is telling us that emptiness has structure without requiring spectacle. Another example comes from the Lamb shift in atomic physics. The energy levels of electrons in hydrogen are altered slightly by their interaction with the fluctuating vacuum. Once again, something that classical emptiness should not contain turns out to matter. The vacuum participates. It contributes. It enters the fine details of reality. And then there is the Higgs field. The Higgs field fills space, and the way particles interact with it helps determine their masses. Without it, electrons and quarks would not behave as they do. Atoms would not form the same way. Chemistry would not proceed in familiar patterns. The stability of matter, as we know it, depends on the structure of what might once have been called empty space. So by now, a strange truth begins to emerge. What seems like nothing is not the opposite of structure. It is the ground of structure. The more carefully we examine emptiness, the more we find the preconditions for everything. That alone would make the vacuum fascinating. But the story becomes even more extraordinary when we ask whether the vacuum carries energy. The answer appears to be yes. And that quiet answer reaches all the way to the scale of the universe. Vacuum energy is one of the most counterintuitive ideas in physics. If empty space is not truly empty, if fields remain and fluctuate even in their lowest state, then the vacuum is not only structured, it also carries a kind of irreducible energy, not the energy of hot gas, not the energy of starlight, not the energy of visible motion, but energy woven into the condition of space itself. This is difficult to picture, and perhaps it should be. Physics often becomes most interesting precisely where imagination has to slow down and become more careful. Yet there are real reasons to take the idea seriously. In the late 20th century, observations of distant supernovae revealed that the expansion of the universe is accelerating. Galaxies are not merely moving apart from one another. On the larger scales, the rate of that separation appears to be increasing. For a long time, many expected gravity to slow cosmic expansion. Matter attracts matter. Galaxies, clusters, and all massive systems should tug against the outward motion. And yet the observations suggested something else. Something was pushing on the scale of the cosmos. Not a push in the mechanical sense, but a contribution to space-time itself that drove accelerated expansion. The name we give this effect is dark energy. Dark energy is not directly seen. It does not emit light. It does not gather into ordinary structures like matter does. We infer it from what the universe does on large scales. One natural candidate for dark energy is vacuum energy. If that interpretation is correct, then the most empty-looking parts of the universe are not passive at all. The quiet background between galaxies is participating in the largest story of all, the fate of the cosmos. That is a remarkable thought to let settle in. The energy of what appears to be nothing may be helping shape everything. And yet, as usual in deep physics, the story comes with a puzzle attached. Calculations of vacuum energy in quantum field theory, done in the most straightforward way, produce values enormously larger than what cosmology seems to observe. The mismatch is vast, one of the worst in all of physics. This is known as the cosmological constant problem, and it remains unresolved. So vacuum energy is not a finished chapter. It is an open one. Still, even unfinished, it teaches us something important. Empty space matters. Its structure matters. Its energy matters. Its hidden properties influence atomic behavior, possibly the acceleration of the universe, and perhaps the deepest questions of cosmic origin. At this point, the next great shift in thought begins to feel less like a shock and more like a natural continuation. If the vacuum is not passive, perhaps space itself is not passive either, and neither is time. This is where relativity enters the story. Before Einstein, it was natural to imagine space and time as a neutral background. Space was the stage on which matter moved. Time was the universal clock ticking above the stage. Forces acted. Objects changed position, but the background remained unchanged. Einstein overturned that picture. In special relativity, space and time became interwoven. Measurements of length and duration depended on motion. There was no longer one universal clock running the same way for everyone. In general relativity, the change went deeper still. Gravity ceased to be understood as a force acting across an empty gap in the old Newtonian sense. Instead, matter and energy curve spacetime, and that curved spacetime tells matter how to move. Geometry became physical. The stage joined the drama. That phrase is worth lingering on because it is one of the great transformations in the history of thought. The world is not just things moving through a passive emptiness. The emptiness itself has geometry. The geometry itself evolves. That is why light bends near massive bodies. That is why clocks run at different rates in different gravitational fields. That is why black holes can exist. That is why gravitational waves ripple through the universe. And that is why the universe itself can expand. This last idea is so important and so often misunderstood that it deserves to be approached gently. When people hear that the universe is expanding, they often imagine an explosion, matter flying outward into a pre-existing void, a center somewhere from which everything is rushing away, a cosmic blast. But that is not what modern cosmology means. The Big Bang was not an explosion in space. It was the expansion of space. This is a subtle distinction, but it changes everything. To understand how we learned this, it helps to go back to the early 20th century, when astronomers were still debating the true scale of the universe. The Milky Way was known. Stars filled the sky. Faint spiral nebulae could be seen through telescopes. But what were they? Nearby clouds? Or entire galaxies beyond our own? Edwin Hubble helped answer that question by using Cepheid variable stars as distance markers. He showed that Andromeda was not a local cloud inside the Milky Way. It was another galaxy entirely. The universe suddenly became much larger than previously imagined. Then came the redshifts. The light from distant galaxies was stretched toward longer wavelengths. The farther the galaxy, the greater the redshift tended to be. This relation became known as Hubble's law. The natural interpretation was that the universe is expanding, not from a special center, not into some outside space, but everywhere, on large scales, because the distances between galaxies are growing as space-time itself expands. This transformed cosmology into history. If the universe is expanding now, then, in the past, it must have been smaller, hotter, denser, more compact. Run the story backward far enough, and the galaxies approach one another. The temperature rises, the familiar structures of the present dissolve, and the universe becomes a very different place. This is the path to the Big Bang. And again, the name is more dramatic than the idea itself. The Big Bang is not a fireball exploding into emptiness. It is the name we give to the hot, dense early phase of an expanding universe. The model tells us that the cosmos was once much hotter and denser than it is now. As expansion continued, it cooled, particles formed, nuclei formed, later atoms formed. Radiation decoupled from matter. Light began traveling freely across space, over immense stretches of time. Gravity amplified tiny density differences into stars, galaxies, and larger structures. This framework is supported by several powerful lines of evidence. The abundance of light elements, such as hydrogen and helium, matches expectations from a hot early universe. The cosmic microwave background is relic radiation from that early phase, stretched by cosmic expansion into microwaves. The recession of galaxies fits naturally with the overall picture. Together, these facts make the Big Bang one of the most successful scientific theories ever developed. But it is not a complete explanation of everything. If we push the equations of general relativity backward too far, they point toward a singularity, where density and curvature become infinite. Most physicists do not take that as a final, literal description of reality. Instead, the singularity is seen as a sign that our current theory has reached the edge of its domain. Near such extremes, quantum effects should matter too, and we do not yet have a universally accepted theory that unifies quantum mechanics and gravity. So the Big Bang is not yet a theory of absolute origin. It is a theory of early evolution. It tells us how the universe developed from a very early, hot, dense condition onward. It does not yet tell us, in a final sense, why there is a universe at all, or what the deepest beginning really was. Even as a theory of early evolution, the Big Bang left some puzzles. Why is the universe so uniform on very large scales? Distant regions of the cosmic microwave background have nearly the same temperature, even though, in the simplest version of the story, they should not have had enough time to influence one another. Why is the geometry of the universe so close to flat? Why are certain exotic relics not seen? These puzzles led to one of the boldest ideas in modern cosmology: inflation. Inflation proposes that in the earliest fraction of a second, the universe underwent a period of extremely rapid, exponential expansion. A tiny patch of space-time may have stretched enormously in a moment, so brief that ordinary language can barely hold it. This idea solves several problems at once. If the region that became our observable universe was once much smaller, then different parts of it could have been in contact before inflation stretched them apart. That helps explain the smoothness of the cosmic microwave background. Inflation also drives the geometry of the universe toward flatness, much as the surface of a giant sphere looks flatter and flatter over any local patch. And it dilutes unwanted relics, spreading them across such a vast volume that they become effectively invisible. But inflation does more than solve problems. It creates seeds. Quantum fluctuations in the early universe, ordinarily microscopic, would be stretched by inflation to cosmic scales. Tiny irregularities in a field become tiny irregularities in density. Those density differences survive after inflation ends. Gravity later amplifies them. Slightly denser regions attract more matter. Matter gathers, structure grows. Galaxies begin as faint unevenness. Clusters begin as subtle ripples. The large-scale structure of the universe may be the expanded memory of quantum fluctuations. There is something deeply elegant about this. The smallest scales speaking to the largest. The early universe whispering to the later one. The cosmic microwave background preserves evidence of this process. It is nearly uniform, but not perfectly so. Tiny temperature variations correspond to tiny density variations. Those became the seeds of everything that came later. Without them, the universe might have remained smooth and dull. No galaxies, no stars, no planets, no chemistry rich enough for life, no minds asking questions about nothing. It is because perfect sameness was broken ever so slightly that the universe became capable of complexity. Dark matter likely played an important role in this process as well. Because it does not interact with light the way ordinary matter does, it could begin clumping earlier, forming the invisible scaffolding into which ordinary matter later fell. The galaxies we see may be luminous patterns arranged on top of an unseen framework. So when we look at the night sky, we are not looking at a random collection of isolated objects. We are looking at outcomes, at memories, at structures whose ancestry reaches back to the earliest moments of cosmic history. A galaxy is not merely a group of stars. It is a late consequence of early irregularities. A star is not merely a glowing sphere. It is part of a story that begins in the vacuum, in fields, in fluctuations, in the hot early universe. In that sense, the visible universe is the long unfolding of hidden beginnings. This leads naturally to another subtle question. If a universe like ours emerged from a vacuum state, from fields and fluctuations, and expanding spacetime, does that violate conservation laws? How can an entire cosmos appear without requiring an impossible supply of energy from outside? This is where gravity changes the emotional tone of the question. Matter and radiation carry positive energy. Gravity is more subtle. Gravitational potential energy is negative. Bound systems, like a planet orbiting a star, have lower total energy than separated systems. The attractive nature of gravity makes the bookkeeping of the universe different from the bookkeeping of ordinary mechanical systems. Some cosmologists have suggested that the positive energy of matter and radiation might be balanced by the negative energy associated with gravity. If so, the total energy of the universe could, in a meaningful sense, be zero. This is the zero-energy universe idea. In such a picture, the cosmic ledger balances. A universe does not require a net injection of energy from beyond itself. Positive and negative contributions cancel. This is not a trivial claim, and it is not free of technical subtleties. Energy in general relativity is a delicate concept, especially when applied to the universe as a whole. But the idea remains powerful because it shows that the existence of a universe need not obviously violate the conservation laws that guide ordinary physics. Existence may not be a cosmic accounting error. It may be a balanced state. And once that possibility is entertained, the question of origin becomes both softer and stranger. Softer, because the old intuition that you can't get something from nothing becomes less absolute once gravity enters the picture. Stranger, because the kind of nothing under discussion is no longer absolute emptiness, but a structured physical state full of hidden law, hidden geometry, hidden possibility. And then another question rises, perhaps the most elusive of all. What about time? If the universe has a beginning, what does it mean to ask what came before? In daily life, the word before feels obvious. Breakfast comes before lunch. Childhood comes before adulthood. One note comes before the next in a melody. But cosmology is not daily life. Time in relativity is not a universal background flowing identically everywhere. It is part of spacetime. It bends with gravity. It depends on motion. It may not remain meaningful in the familiar way under the extreme conditions of the early universe. So when we ask what happened before the Big Bang, we may already be assuming too much. We may be assuming that time extends backward beyond the earliest state in the same ordinary way that yesterday extends behind today. But if time itself emerged with the universe, then the word before may lose its ordinary meaning. This does not make the question foolish. It makes the question delicate. Some proposals in quantum cosmology try to take this delicacy seriously. The Hartle-Hawking no-boundary proposal, for instance, suggests that near the earliest state, time may behave more like a spatial dimension, smoothing away the idea of a sharp first instant. In such a view, the universe may not begin with a temporal edge in the everyday sense. Other models suggest bounces instead of beginnings, with a contracting phase preceding expansion. Others suggest emergent spacetime, where time and space are not fundamental ingredients but arise from something deeper. Others explore eternal inflation and multiverse ideas, in which our observable universe is one region within a larger process. None of these models is final, but all of them carry the same lesson. Our ordinary intuition about time was formed under calm conditions on a small planet around one star. The early universe is under no obligation to resemble that intuition. There is also another mystery tied to time. Why does it seem to flow in one direction? At the microscopic level, many physical laws do not distinguish strongly between past and future, yet experience does. Glasses shatter, ice melts, heat spreads, memories point backward, not forward. This arrow of time appears deeply connected to entropy and to the fact that the early universe seems to have begun in a very low entropy state. Why that was so remains one of the deepest questions in cosmology. So the moment we ask about nothing, we are led into the structure of time itself. And when we follow time toward its own beginning, we arrive at the singularity. General relativity, extraordinary though it is, predicts its own breakdown under sufficiently extreme conditions. At the centers of black holes and at the backward edge of the expanding universe, curvature and density appear to become infinite. Most physicists do not treat these infinities as final truths of nature. They treat them as signs that the theory has reached the edge of its usefulness. At such scales, quantum effects must matter. But general relativity is a classical theory, and quantum mechanics does not yet provide a finished description of space-time itself. This is why the search for quantum gravity remains one of the great unfinished tasks in physics. A successful theory of quantum gravity would tell us how space-time behaves at the smallest scales. It would tell us what becomes of singularities. It would tell us how to describe the earliest universe when quantum fluctuation and space-time curvature matter at the same time. String theory offers one approach. It replaces point particles with tiny, vibrating strings and suggests that familiar particles arise from different vibrational modes. Loop quantum gravity offers another. It attempts to quantize space-time itself, suggesting that space may be discrete rather than continuous all the way down. Other ideas involve holography, causal sets, emergent space-time from quantum information, and other deep frameworks still under development. None has yet become the universally accepted final answer, and that is worth saying plainly. Modern cosmology knows a great deal. It knows the universe expands. It knows the early universe was hot and dense. It knows the cosmic microwave background preserves a memory of that past. It knows structure grew from tiny irregularities. It knows empty space is not truly empty. It knows space-time is dynamic. It has evidence that cosmic expansion is accelerating. But at the deepest edge, where gravity and quantum theory must be unified, the map is unfinished. That is not failure. It is the frontier. And perhaps that brings us back, one final time, to the original word. Nothing. What do physicists really mean by it? Usually, they do not mean absolute non-existence. They do not mean the total absence of space, time, law, structure, and possibility. They mean the emptiest, physically describable state. A vacuum, a ground state, a condition in which there may be no ordinary particles present, yet fields remain, fluctuations remain possible, energy may remain, and space-time itself remains part of the story. That is not nothing in the everyday sense, and it is certainly not nothing in the absolute philosophical sense. It is subtler than that, quieter, thinner, more minimal, but still real. And once that becomes clear, many famous cosmic questions change their tone. Could the universe emerge from a quantum vacuum? In some physical models, perhaps. Could quantum fluctuations seed galaxies? Modern cosmology strongly suggests that something like this happened. Could empty space carry energy that influences cosmic expansion? Very likely, in some form. Could the total energy of the universe balance to zero? Possibly. Could time itself be part of what emerges rather than a pre-existing backdrop? Some of our best ideas point in that direction. But can physics yet explain why there is something rather than nothing in the deepest philosophical sense? Not fully, and perhaps not yet at all. There is something honest and strangely comforting about that limit. Science grows stronger, not weaker, when it knows exactly where its present language becomes uncertain. What physics has done is not to eliminate the mystery of nothing. It has transformed it. It has taken a word that once seemed empty and discovered layers inside it. Ordinary emptiness turned out to contain air, heat, radiation, and matter. The vacuum chamber turned out to contain fields. The fields turned out to fluctuate. The vacuum turned out to carry energy. Space-time turned out to be dynamic. The early universe turned out to preserve the seeds of galaxies. Time turned out not to be simple, and the boundary between nothing and something turned out to be much softer than everyday language suggests. Perhaps that is the quietest lesson of all. The universe does not become simpler when we strip away appearances. It becomes deeper. Each time we think we have reached emptiness, we find one more layer still there. Atoms, fields, fluctuations, geometry, energy, symmetry, possibility. And maybe that is why this question has lasted for so long. Because it is not only a question about cosmology, it is a question about how far our words can go before they need to be refined. We say empty, and physics asks, empty of what? We say beginning, and physics asks, beginning in what sense? We say before, and physics asks, what do you mean by time? We say nothing, and physics asks, which nothing? That is not frustration. That is understanding becoming more precise. And there is something peaceful in that precision. The world is not shallow. The darkness between stars is not dead. The vacuum is not mute. The invisible is not secondary. What looks like absence may contain the quiet conditions from which structure, history, and meaning emerge. The visible universe is full of things that draw the eye: stars, galaxies, nebulae, planets, the glowing edge of worlds, the bright trails of comets, the soft blue light of Earth from orbit. But beneath all of that is a subtler layer of reality, one that does not appear to the senses in any simple way. A layer of fields, vacuum states, fluctuations, geometry, symmetry, broken symmetry, energy hidden in emptiness. And from that deeper layer, slowly and patiently, the visible universe unfolds. Perhaps the best place to end is where we began, with the room, the quiet room that seemed empty at first glance. The shelves bare, the floor clear, the air removed, the silence deepening. And then, slowly, the realization that the room was never truly empty in the way we first meant. There was still structure, still radiation, still the possibility of fluctuation, still the hidden presence of fields, still the faint hum of reality in its most minimal known form. That room is not the whole universe, but it teaches the lesson. What looks like nothing is often the beginning of better seeing, and on the largest scale, that may be true as well. The darkness between galaxies is not mere blankness. The vacuum is not mere absence. The early universe was not a simple void. What appears to be nothing may be the faintest layer of a deeper something. And from that faint layer, under laws we only partly understand, stars ignite, galaxies gather, time unfolds, matter organizes, life appears, and minds arise that are capable of looking back across billions of years and asking the question from which we started. What is nothing? Perhaps the calmest answer physics can presently offer is this. Nothing, in the scientific sense, is not the absence of all reality. It is the most minimal form of reality we currently know how to describe. A ground state, a vacuum, a quiet sea of fields, a condition thinner than matter, quieter than light, yet still structured, still lawful, still carrying possibility. And even that most minimal condition is richer than anyone once imagined. The empty room was never truly empty. The silent vacuum was never truly silent. And what once looked like nothing may have been, all along, the quiet beginning of everything. And perhaps the strangest part of this story is that the deeper physics goes into emptiness, the more it finds not less reality, but more layers of it. At first, this feels almost backward. Human intuition usually moves in the opposite direction. We think that if we keep removing things, reality should become simpler and simpler until eventually nothing is left. Remove the furniture from the room. Remove the air. Remove the dust. Remove the heat, the light, the noise, the matter. Keep stripping things away, and surely the world must eventually collapse into a perfect blank. But the history of physics has not followed that path. Instead, each time science has stripped reality down, a subtler layer has remained behind. When visible objects were removed, air remained. When air was removed, radiation remained. When matter was removed, fields remained. When particles were removed, fluctuations remained. And when even the vacuum was imagined as the quietest possible state, that quiet state turned out to carry structure, energy, and consequences of its own. So perhaps emptiness is not a destination at all. Perhaps it is a moving horizon, a concept that recedes each time understanding advances. There is something deeply revealing in that idea, because it tells us that the question of nothing is not merely about origins. It is also about how knowledge works. It is about what happens when intuition meets precision. It is about how the universe repeatedly refuses to match the first draft of our language. And nowhere is that more apparent than in the relationship between the vacuum and the cosmos as a whole. It is one thing to say that empty space is not truly empty in an atom or inside a laboratory chamber. It is another to say that the character of empty space may help determine the entire history of the universe. Yet that is exactly where modern cosmology leads. Consider, for a moment, the early universe not as a place full of stars and planets, but as a much simpler and much stranger environment. There were no galaxies yet, no long-lived structures, no heavy elements, no oceans, no worlds, only an expanding sea of energy, particles, radiation, and fields in extreme conditions. What matters in such an environment is not merely what objects exist, but what the vacuum itself is like. Because the vacuum is not a passive backdrop, it is a state of the fields. And the state of those fields influences what kinds of particles can exist, what masses they have, how they interact, how symmetry is broken, how energy is distributed, and how the universe evolves. This is one reason the idea of phase transitions in the early universe has become so important. In ordinary life, a phase transition is something familiar. Water freezes into ice. Ice melts into liquid. Liquid becomes vapor. The substance remains, but the state changes, and with the state come new properties. A frozen lake is made of the same molecules as liquid water, yet its structure and behavior are profoundly different. Physics suggests that the early universe may have gone through transitions of its own, not involving water, of course, but involving fields and symmetries. At extremely high energies, the laws of nature may have looked more unified than they do now. As the universe expanded and cooled, that high-energy order may have broken into the distinct forces and particles we now observe. And once again, the vacuum is central. Because what changes in such a transition is not merely what particles happen to be present. What changes is the state of the fields themselves. The vacuum before the transition and the vacuum after the transition may not be the same. That thought can feel abstract at first, so it helps to slow it down. When physicists speak of a vacuum state, they do not mean only empty space. They mean the lowest energy arrangement available to the fields under certain conditions. And there may be more than one such arrangement in principle. Reality might occupy one vacuum state rather than another, and the difference between those states can shape the entire character of the universe. The Higgs field offers one of the clearest examples of this. In the early universe, before certain symmetries were broken, the Higgs field may not have sat in the same state it occupies now. As conditions changed, the field settled into a new vacuum state, and with that settling came the masses of particles as we know them. The universe did not merely cool in the ordinary thermal sense. It changed character. This is one of the most beautiful ideas in modern physics. The cosmos is not just a collection of things moving through time. It is a history of states, a history of transitions, a history in which the very vacuum has a role to play. And that brings us to another subtle possibility, one that physicists discuss carefully and usually with more calm than popular headlines allow. What if the vacuum state we inhabit is not the only one possible? In some theoretical frameworks, the vacuum we experience could be what is called a metastable state. Not the absolute lowest conceivable state, but a locally stable one, a bit like a ball resting in a shallow valley, rather than the deepest valley in the entire landscape. Such a state can persist for immense stretches of time, so long that for all practical purposes, it behaves as stable. Yet in principle, a deeper vacuum state might exist. This idea is sometimes described in terms of false vacuum and true vacuum, though the word false should not be taken to mean unreal. It simply means not the ultimate minimum of the energy landscape. This concept opens the door to the notion of vacuum decay, in which a transition to a lower energy state could occur. Popular treatments often describe this in alarming ways. But within the calm spirit of scientific understanding, it is better to see it as one more expression of how rich the concept of vacuum has become. The very fact that empty space can be discussed as having states, landscapes, and possible transitions tells us how far modern physics has moved from the older image of a blank void. In reality, there is no reason to live in anxiety over such possibilities. If such transitions are possible at all, they are expected to be unimaginably rare on human timescales. More importantly, the concept matters because it shows how the vacuum has become something like a character in the story of the universe, rather than merely a stage. And the more we allow that perspective to settle, the more the history of cosmology begins to feel unified. The vacuum is not separate from particles. Particles are excitations of fields. Fields are not separate from spacetime. Spacetime is not separate from cosmic expansion. Cosmic expansion is not separate from the early universe. The early universe is not separate from the origin of structure. And structure is not separate from the existence of stars, planets, chemistry, biology, and the quiet rise of minds capable of asking questions. One layer flows into the next. One idea leans into another. The visible universe rests on an invisible continuity. This is especially striking when we think about the cosmic microwave background. The microwave background is one of the gentlest pieces of evidence in science. It is not spectacular in the ordinary sense. It is not a blazing object in the sky. It is a faint glow, almost uniform, filling all directions, a quiet remnant from the time when the universe became transparent to light. And yet, In that faint glow, the early universe still speaks. Its tiny temperature variations, measured with astonishing precision, show us that the young cosmos was not perfectly uniform. It was almost smooth, but not completely. Slight differences existed. Slight density contrasts were already there. These are not large features, they are minute. But over cosmic time, minute differences are enough. Gravity is patient. Given enough time, a small excess of matter in one place becomes a slightly stronger pull. That stronger pull gathers more matter. More matter means more gravity. More gravity means more gathering. A tiny unevenness grows into a cloud into a proto-galaxy into a galaxy into a larger structure surrounded by many others. The universe does not need dramatic beginnings in order to achieve dramatic outcomes. Sometimes all it needs is a little asymmetry and a very long time. There is something deeply peaceful in that thought. Complexity need not arrive with violence. It can arrive with patience. It can arrive through amplification, through time, through small differences carried forward. And this brings us back to one of the most extraordinary implications of inflation and quantum cosmology. The structure of the universe may be the amplified record of quantum uncertainty. That sentence deserves to be felt slowly. The same kind of underlying uncertainty that appears in the behavior of microscopic systems may have left its mark on the scale of galaxies and clusters. The placement of large-scale structure in the universe may trace back, in a meaningful way, to tiny fluctuations stretched by inflation into cosmic size. In that sense, the night sky is not only a display of, it is a fossil record of early possibility. The galaxies are not merely objects. They are memories. Memories of a time when the universe was young enough for quantum fluctuations to become the seeds of everything that followed. And perhaps that is one reason the question of nothing leads so naturally into a kind of quiet awe. Because it reveals continuity where intuition expects disconnection. We imagine nothing and something as opposites, separated by a hard line. Physics instead suggests a layered transition. Ground state to fluctuation. Fluctuation to density difference. Density difference to structure. Structure to stars. Stars to elements. Elements to planets. Planets to chemistry. Chemistry to life. Life to consciousness. Consciousness to questions. The line between nothing and something becomes less like a sharp border and more like a gradual unfolding. This does not solve the deepest philosophical problem, but it changes the atmosphere around it. It makes the universe feel less like a magician's trick and more like a long, lawful emergence. And that lawful quality matters. It is one of the reasons science can speak meaningfully at all. Physics does not merely say that things exist. It says that things exist in patterns, under laws, with regularities that can be studied. When cosmologists trace the universe backward, they are not inventing a story from pure imagination. They are following evidence, redshifts, background radiation, element abundances, structure formation, supernova observations, gravitational theory, particle physics. There is still mystery, yes, but it is a disciplined mystery. A mystery mapped by equations, constrained by data, sharpened by observation. That kind of mystery is not the darkness of ignorance. It is the twilight of the frontier. There is another place where the richness of the vacuum reveals itself, and that is in the study of black holes. Black holes are often imagined as pure endpoints, objects so extreme that they swallow everything and give nothing back. In the classical picture, that is almost true. A black hole is defined by an event horizon, a boundary beyond which escape is impossible. Not even light, once past the horizon, can return to the wider universe. And yet quantum theory changes this picture too. Stephen Hawking showed that black holes are not completely black when quantum effects are taken into account. Near the event horizon, the vacuum behaves differently from the way it does in empty, flat spacetime. Fluctuations in the vacuum, together with the curved geometry, can lead to the appearance of radiation escaping from the black hole. The details are subtle, and the simplified image of one particle falling in while another escapes should be treated as only an approximation to a deeper calculation. But the lesson remains. Even black holes cannot fully escape the richness of the vacuum. The quiet structure of empty space still matters there. And over unimaginably long times, that subtle radiation could allow black holes to slowly lose energy and evaporate. This is one of the most astonishing examples of how quantum theory and gravity, even before they are fully unified, already hint at a deeper picture. The vacuum is not absent even at the horizon of a black hole. The universe does not allow the old image of empty nothingness to return, even in the darkest places. In a way, that is the recurring theme of modern physics. The void keeps refusing to be void. Empty space keeps refusing to be merely empty. The background keeps revealing itself as active, and the further this idea develops, the more it changes how we think about beginnings. The Big Bang itself is often misunderstood because the word bang suggests a loud event inside some larger emptiness. But there was no outside space waiting to be filled in the ordinary sense. Space-time itself was part of the evolving system. The early universe was not a fireball exploding into a room. It was a rapid change in the geometry and state of the cosmos itself. This matters because it reshapes the question of origin. If space-time itself evolves, then asking what the universe expanded into may be like asking what lies beyond the surface of a balloon if one lives entirely on that surface. The question may be importing an outside perspective that the system itself does not contain. Likewise, asking what happened before time began may use the word before too easily. Time, in modern cosmology, is not automatically something outside the universe. It may be part of what the universe is. This is one reason why cosmological questions often feel philosophically charged. They force us to notice how much of our thinking depends on grammar and intuition shaped by ordinary life. Before and after, inside and outside, empty and full, cause and effect. These words work beautifully within the world of human scale. But at the edge of cosmic origin, they sometimes have to be handled more delicately. That delicacy is not a weakness. It is a sign that understanding is becoming more careful. And careful understanding is one of the most calming things science can offer. It allows us to see where our first intuitions hold, where they fail, and where new concepts must take their place. So where does all of this leave the original word? Nothing. By now, it should feel transformed. Not destroyed, not discarded, but refined. Nothing in everyday speech can still mean an empty drawer, an unused seat, a quiet room, an empty road at night. Ordinary language is not wrong. It is simply tuned for ordinary life. Nothing in physics means something else. It means the nearest approach to emptiness that a lawful universe seems to allow. A vacuum state, a ground state. A physical condition stripped of ordinary particles, but not stripped of fields, not stripped of possibility, not stripped of structure, not stripped of the potential for fluctuation. This is a very different kind of emptiness. And once we see that clearly, many familiar claims become easier to interpret. The universe may have come from nothing, does not mean the universe came from absolute non-being, with no laws, no space, and no framework. It usually means something like the universe may have emerged from a minimal physical state, such as a quantum vacuum, or a state described by quantum cosmology. That is still extraordinary, but it is not the same claim. The distinction matters because otherwise science is asked to answer a question it may not yet be equipped to frame. Physics can model vacuums, fields, symmetries, geometry, transitions, inflation, and structure formation. It can explore what happens when those ingredients are taken to their limits. But the absolute philosophical question, why there is any reality whatsoever rather than none, may still lie partly beyond the reach of present theory. And yet, even without fully answering that ultimate question, physics has changed the landscape around it. It has shown that empty space is not an obvious concept. It has shown that the vacuum is structured. It has shown that fields cannot be simply wished away. It has shown that quantum fluctuations have measurable effects. It has shown that the expansion of the universe may be linked to the properties of empty space. It has shown that the large-scale structure of the cosmos may descend from small early fluctuations. It has shown that space-time itself is dynamic. It has shown that time may not be a simple background. It has shown that the deepest layers of reality are quieter, subtler, and more active than common sense once supposed. Perhaps that is why the question of nothing remains so beautiful, because instead of leading us into blankness, it leads us into depth. Instead of emptying the universe of meaning, it reveals the hidden architecture beneath appearance. Instead of ending inquiry, it begins it. And perhaps the most peaceful way to hold all of this is not to demand a final answer too quickly. Not every great question is improved by forcing it into a conclusion before the evidence is ready. Some questions become more beautiful when they are allowed to remain open in disciplined ways. What is nothing? Physics can now answer part of that. Nothing, in the scientific sense, is not a total void. It is not the abolition of all being. It is a minimal physical state, a vacuum, a ground level of fields and structure, a condition quieter than matter and radiation, but not free of law or possibility. Why is there something rather than nothing? Physics can circle that question, sharpen it, illuminate some versions of it, and perhaps one day go further than it can now. But, for the moment, the deepest philosophical version remains partly open. And openness, when it is honest, is not a defect. It is part of what keeps wonder alive. If everything were already settled, curiosity would have nowhere to go. Instead, we find ourselves in a universe where the visible world rests on invisible order, where emptiness is active, where silence has texture, where the dark between galaxies may contain the energy that shapes the future, and where a simple room that looked empty became the first clue that nothing is one of the richest ideas in all of science. So perhaps, as the thought settles, the best image to carry forward is still that first one. A quiet room, bare shelves, a swept floor, still air, or no air at all. And then, slowly, the realization that even there, even in the most unassuming emptiness we can imagine, reality remains. Heat whispering from the walls, fields extending through space, the possibility of fluctuation, the faint hum of a lawful universe. What looked like absence turns out to be only the thinnest layer of presence. And the same may be true everywhere. The vacuum of physics is not the end of explanation. It is where some of the deepest explanations begin. The more gently we look, the more there is to see. The more carefully we strip away appearances, the more we find that the universe is not built on blankness, but on a quiet, structured depth that was hiding there all along. And that may be the calmest answer physics can presently offer. Nothing, in the scientific sense, is not the absence of reality. It is the faintest, quietest, most minimal form of reality we know how to describe. And even that faintest form is full of more than anyone once imagined.